Continuing on physical chemistry, chapter 8, we're beginning section 2 now. So let's say we want to talk about the pressure of an ideal gas. So we say that it's equal to the pressure of a real gas versus plus correction terms. Or we could say the pressure of a real gas is equal to pressure ideal minus correction terms. So let's just say from now on, P is the real gas. So pressure of a real gas is equal to nRT over V minus NB minus N squared A over V squared, where B is the volume occupied by 1 mole, and this is characteristic of gas. That means it's specific to the gas. Now, the volume of the real gas is less than the volume of the ideal gas, because NB is the space actually occupied by the volume. So V minus NB is the available volume. Then the N squared A over V squared term is the correction for intermolecular attractions. Now the attractions reduce pressure, which hence the minus sign in the equation. You subtract it out. Like I said, both A and B, they're constants and they're specific to the gas. We're going to divide by the last term by N on the top and bottom, and we're going to divide the right term by N squared on the top and the bottom. So we're going to get pressure is equal to RT over molar volume minus B minus A over molar volume squared. So now we're going to add the we're going to move this over here and then multiply. So we're going to get pressure plus A over molar volume squared times molar volume minus B equals RT. This is called the van der Waals equation. Actually, I think it's van der Waals equation, I'm not sure. Anyway, if A is equal to 0 and B is equal to 0, then you notice this disappears, disappears, and it just becomes pressure molar volume is equal to RT. This is the formula for an ideal gas. Now we're going to solve for molar volume. So molar volume is equal to RT over pressure plus A over molar volume squared plus B. Now we're going to take the limit as pressure approaches infinity, and the molar volume is B. See what I mean? So if you say pressure approaches infinity, then this whole term becomes infinity. This whole term becomes 0. So the molar volume is just equal to B. Now you don't ignore this molar volume squared down here, because remember, the bigger molar volume we get, this squared is going to make this 0, so it'll be kind of negligible. Now, Vm, the molar volume, can't be less than B. I'm going to take the limit of P as the molar volume approaches infinity. So you get P is equal to RT over molar volume minus B minus A over Vm squared is roughly equal to RT over Vm. So basically what that's saying is when molar volume gets really big, this term will be a lot bigger than this one, so we can neglect this term. So that's why it just drops off and we end up with this. And likewise, molar volume will be so much bigger than B that it just becomes molar volume here. So we can simplify. So as molar volume increases, the pressure decreases. Now, let's assume that we have two identical spherical molecules, kind of like a noble gas, like neon or something. So they're touching here. Each one has its own radius. So the difference between the center to center will be delta. Oh no, sigma. Okay, it looks like a delta. Anyway, so R is radius and sigma is the diameter. Now the shaded area, see how it goes all the way from the diameter out from one molecule? This is the excluded volume for that one molecule. So like I said, the sigma is equal to 2 times the radius. So the excluded volume per molecule is basically the volume for a sphere of radius sigma. So we have 4/3 pi sigma cubed times 1/2. And that is equal to B. So, okay, why did I make such a mess here? So we get 4/3 pi 2r cubed times 1/2 equal to 4 times 4/3 pi r cubed. Oh no, wait a minute. This is actually, B is all that times Avogadro's number. So that's why I crossed out the B here. So this probably isn't actually equal to B. So we'll say times NA equals B. So I know next time. Okay, so the excluded volume is 4 times the volume of each molecule. That's why we left it with the 4 factored out like that, because the volume of the sphere is this big, and the excluded volume is this big. Okay, so because of the volume of one molecule is 4/3 pi r cubed. So B is 4 times the atomic volume per mole, or 4 times the molar volume per mole. So B is normally found experimentally. We can curve fit it from data, and it's going to be in units of liters per mole or centimeters cubed per mole. Now, of course, the way we calculated it only works for spherical molecules. And then A is going to be in liters squared times atmospheres per mole squared. Now, the van der Waals equation is semi-empirical equation because partly theoretical and partly experimental. Now, in nonpolar molecules, intermolecular attractions are caused by the London force, the polarizability. Now, let's talk about the van der Waals constants. So we'll compare a few gases here. So for helium, A is 0.034, B is 0.0237. The units I already told you what that is. Neon is 0.244 and for A, and then B is 0.0266. And then carbon dioxide is 3.59, and B is 0.0427. So remember, curve fitting is when you match a model to experimental data. In addition to the van der Waals equation, we also have the Redlich-Kwong equation, where that's pressure is equal to nRT over V minus NB minus n squared A over temperature to the 1/2 power times V plus NB times V. Notice this has constants A and B in it, but these are going to be different constants from the van der Waals equation for any gas. There's also the Berthelot equation. That's pressure is equal to nRT over volume minus, NB, minus n squared A over TV squared. Now back to the van der Waals equation. With the bigger molecule, that means a larger A, so stronger intermolecular forces. But with a bigger molecule also means larger B, which means it actually takes up more volume. Another equation of state is the Virial equation. So we're going to have the Virial equation, the Virial series, which is an equation. Virial means force, which means Latin. So it's an equation based on the forces. Now remember, the compressibility Z is pressure times molar volume divided by RT, and that's equal to 1 for an ideal gas. See handout 40. Now we're going to expand Z as a power series. Now remember, N over V is the reciprocal of molar volume. So N over V is equal to 1 over molar volume. We're going to write the compressibility is equal to 1 plus B of temperature times N over V plus C of temperature times N over V squared plus D of T times N over V cubed, etc., etc., etc. Or you could write that Z is equal to 1 plus B of T over the molar volume plus C of T over the molar volume squared plus D of T over the molar volume cubed, etc., etc. So this 1 we say is the first virial coefficient. This B is the second virial coefficient. C is the third virial coefficient. D is the fourth virial coefficient, etc. See handouts 32 and 38. Now B and C are both important and temperature dependent. Now we're going to use a little cross sign to mean that they're not the same. So we're going to have Z is equal to 1 plus B cross of T times pressure plus C cross of T times pressure squared plus D cross of temperature times pressure cubed, etc., etc. So we expanded it same as the other one, except here we expanded it based on pressure instead of molar volume. So there is a relation between the two. For B cross, it's just B over RT. For C cross, it's C minus B squared over R squared T squared. So I'd like to see you do D. So if pressure is low, like less than 2 atmospheres, then pressure times the molar volume is equal over RT is equal to 1 plus B over RT times pressure plus C minus B squared over R squared T squared P squared plus etc., etc. So pressure molar volume is equal to RT plus B. Now, as it gets bigger and bigger, that the terms get more complicated. We just neglect the later terms and we stick with the simpler ones. For pressure roughly equal to 2 atmospheres or less and moderate temperature, then we will just have to consider the first few terms. So Z is going to be 1 plus B cross of T times P plus C cross of T, P squared, and ignore the rest. Now we're going to replace Z with pressure times molar volume over RT. So pressure molar volume over RT is equal to 1 plus B over RT times pressure plus C minus B squared over R squared T squared times P squared, etc., etc. So we're going to multiply by RT. So we're going to go pressure times molar volume equals RT plus BP plus C minus B squared over RT, blah, blah, blah. So at higher and higher temperature, this term will become negligible. So that'll give us pressure times molar volume equals RT plus BP. So solving for molar volume, we just have RT over P plus B. So B is the correction term to an ideal gas equation. So here's an example of a typical gas showing B against temperature. So notice it starts out negative, it goes 0, and then positive. So remember, B is dependent on temperature, obviously. There's a special case where B is equal to 0. This is T sub B, and it's called Boyle's temperature. So T sub B, or Boyle's temperature, is where B is equal to 0. At T sub B, the gas is behaving like an ideal gas. See handout 33. Now, back to the van der Waals equation again. We have B is equal to lowercase b minus ART, or A over RT. And this is the same A and B as the van der Waals equation. So we'll set this capital B is equal to 0 to find what is the Boyle's temperature. So we get B equal to B minus A over RT is equal to 0. Solving for TB, we get A over RB. So Z is, remember, was defined, the compressibility is pressure times molar volume over RT. This is for Z ideal. So P is equal to RT over molar volume minus B minus A over Vm squared. That gives us pressure times molar volume is equal to RT molar volume divided by molar volume minus B minus A over molar volume. So we're going to divide that by RT, and we'll get pressure times molar volume over RT is equal to molar volume divided by molar volume minus B minus A over RT molar volume. So now we're going to talk about the compressibility of a real substance. So we have the molar volume divided by molar volume minus B minus A over RT molar volume. Remember, Z ideal is just equal to 1. So now we're going to divide by molar volume. So we get Z real is equal to, we're going to factor out the molar volume. Okay, so we're going to get 1 over 1 minus B over molar volume minus A over RT molar volume. Now this term over here, B over molar volume, is less than 1. Now let's talk about gas mixtures. So remember, chi-I is the mole fraction of substance I. So there's A1 and B1 in gas 1. And then chi2 is the mole fraction. There's A2, B2 in gas 2. Okay, so the absolute value of chi is less than 1. So we expand that using 1 over 1 minus x is equal to 1 plus x squared plus x cubed, etc. We're expanding this term. We're approximating how to calculate it. So A is equal to chi-I squared A1 plus chi2 squared A2 plus 2 chi1 chi2 times A1 A2 to the half power, the square root of this. And the B is going to be chi1 B1 plus chi2 B2. Now that's only for spherical molecules, such as methane or, what is this, benzene, sulfur hexafluoride. Now remember, molar volume is equal to the volume divided by the total number of moles. So we have 1 over 1 minus B over molar volume is equal to 1 plus B over molar volume plus B over molar volume squared plus B over molar volume cubed, etc., etc. Expansion series. So the compressibility of a real gas is equal to 1 plus B over molar volume plus B over molar volume squared plus etc., etc., and then minus A over RT molar volume. Now the compressibility of a real gas then is 1 plus B minus A over RT times 1 over molar volume, which is factored out the molar volumes, plus B squared minus A over molar volume RT, factor out the molar volume. And remember, capital B is going to equal to B minus A over RT. So we're going to say the compressibility of a real gas is just 1 plus B over molar volume plus C over molar volume squared. Therefore, we can say that capital B is equal to lowercase b minus A over RT. So the Boyle's temperature is equal to A over RB. So if BRT is greater than A, then repulsive forces dominate. If BRT is less than A, then the attractive forces dominate. If temperature is greater than Boyle's temperature, then repulsive forces dominate. If temperature is less than Boyle's temperature, then attractive forces dominate. That's all for section 2.